Good morning. I'm Miki Banu. I'm the Technology Director for the Electrical Vehicle Center. We would like to thank very much to Professor Solomon Adera for this great opening today. Of course, we are in Michigan, and anytime, any day we can wait, we can expect or not expect freezing rain. So this is happening today, and that is why we have this switch in our program. And I think we are very flexible. We just show how the EV Center is very robust. I'm very pleased to present you two of the pilot projects. So as you know, the strong components of the Electrical Vehicle Center is developing projects which are advancing technologies for electrification. And within the first prioritization workshop last year in October, we selected a certain number of projects, and thanks to all your votes, because there are industry-led projects. So a project is formed of a consortium, faculty members of the University of Michigan, together with the students. They are put together with industry members in that project to drive some discoveries and realization of the solutions that the industry are needing. So in the prioritization workshop, we decided that two of the projects will be the pilot to demonstrate how a project in EV Center will be developed and how we can expand in achieving different kinds of milestones. Today, we are very proud to show you almost 6 months now since they started their results, and to demonstrate that EV Center is very committed on very fast-paced results. I am very pleased to introduce today these two pilot projects, which are belonging to two research directions. One is drives and machines, and one is batteries. And with this, I would like to introduce the first PI, Professor Heath Hofmann, Professor of Electrical Engineering and Computer Science at the University of Michigan, and through courtesy, Professor of Naval Engineering. Also, Heath Hofmann is our pillar leader for drives. He will introduce to you the first results, I should say, breaking the ice for presenting results within the EV Center, because up to now we talk about organization. Now we are going to actions, results. Professor Heath Hofmann.
So good morning, everyone. My name is Heath Hofmann, and I'm a professor here at Michigan in electrical computer engineering. My research area is electromechanical systems, and I have specifically focused on electric drives for electric vehicles for going on 3 decades now. So this is a topic that's very near and dear to my heart, and so I am the technical lead for the electric machines and drives thrust area within the center. So, a lot of the discussions that are going to happen today are going to focus a lot on battery technologies, and that's actually very appropriate, right? A lot of the challenges we have with EV adoption are related to, batteries, the range, charging time. But there are other aspects of the vehicle that are important as well. The electric drive, for example, is what actually causes the vehicle to move. So you can argue that's a pretty important aspect of the vehicle itself, right? So we're going to talk about electric drive. So I will start off by talking about the pilot project that Miki mentioned, a high power motor with current ripple reduction technology. I'm also going to comment, in addition to the pilot project, we actually have also started 2 roadmap projects, and I'm going to give a brief introduction to those projects as well, okay? But first, let me try and talk a little bit about what an electric drive is. So I have a figure here. So we have the battery pack, which is where we're storing the energy. To propel the vehicle, we have an electric motor. The electric motor is usually what we call an AC motor, alternating current motor, 3-phase typically. The battery stores electricity in a DC form. And so we need something that will convert the DC energy in the battery into AC power that we can provide to the electric motor. That's done through what's called an inverter, which converts DC to AC. The inverter also, through control techniques, is used to actually directly control the torque output of the electric motor as well. Okay. So the first project has to deal with the goal is to produce nice AC currents within the machine. Okay, and so ideally we would want a sinusoidal current shown in the green waveform here, nice pure sinusoid. But because of the nature of how the inverter works, that current is never exactly sinusoidal in nature. All right, and so the red waveform is a bit exaggerated, but it shows sort of how the currents actually deviate a little bit from the desired behavior. And that creates all sorts of issues. It creates additional losses. It creates what we call torque ripple in the machine as well, which is undesirable. And the challenge, though, is that as we're trying to increase the power density of these drives and trying to make them more smaller, more cost-effective, one of the things that's allowing us to achieve that is by running the machine at higher and higher speeds, okay? Because mechanical power is torque times speed. So if we can run at higher speeds, we can get more power out of the same sized machine. So we're running at speeds in the tens of thousands of RPM these days, which is quite high. But as you continue to increase the speeds, which also increases the frequencies, this creates more and more issues with current ripple. And so we're at a point where we're going to need to try to looking at sort of alternative approaches to designing these drives in order to mitigate those ripple issues. But at the same time, we want to accomplish that and still have a low-cost product that is acceptable to the industry. So we're in the first stage of this project, and what we're doing right now is we're going through and trying to do a fairly comprehensive analysis of all the potential approaches that we can use to resolve this issue. And we're looking at it from the electric motor side, from the power electronics side, and also from the control side as well, right? There are things we can do on any of these different aspects of the drive in order to achieve this objective. So for example, for the inverter, we can use what are called multi-level inverter topologies, which can produce outputs with a higher degree of resolution. We can look at different winding designs in the machines and use different winding configurations, such as the open winding motor. Looking at the traditional motor has 3 phases. We're looking at machines with different number of phases, 5 and 6, for example, and trying to determine, with these different approaches and with appropriate control techniques, how can we address and mitigate these current ripple issues, and also potentially adding in filters. Filters, usually we try to avoid in industry just because of the additional cost and space required, but they are able to significantly mitigate current ripple, and so that's another aspect that we're going to consider as well. So we are going through the process of investigating all of these approaches. As a part of this, we are creating a sort of a structure that allows us to do a comparative analysis of the different techniques. We are developing different metrics for all the different techniques and the different aspects of the machine, the current ripple metrics, but also other metrics that deal with the complexity of the solutions, which can relate to cost, and also just the amount of materials, like how much semiconductor material do we need for the inverter, how much energy do the filter elements need to store, and come up with a way of optimizing these systems for the different approaches, and then allowing us to compare the different approaches to try to see which one is going to be the actual best solution for industry. As this process, the first year of the project, we're heavily involved in conducting simulation, developing new simulation techniques, and integrating different simulation methods for motors and power electronics, with the goal of using these to perform this comparative analysis and the optimization involved in that. And that will be the first year. And the goal in the first year is to identify one or multiple solutions that industry is interested in pursuing further, and then years 2 and 3 will involve designing and developing and validating prototypes. Okay, that was the pilot project. I want to talk a little bit about the roadmap projects. The Drive 2 project is called X and 1. The idea here, so we have another picture that kind of illustrates the motor and the inverter and the battery, but there are other what we call power electronic circuits in the vehicle as well. Right, so the battery is operating at has a voltage in the area of hundreds of volts. We need to actually reduce that to a voltage that's safer to run throughout the vehicle, to run things like the lights and the air conditioning, and your screen. And so we need to have a DC-DC converter to reduce the voltage down to something that's a bit safer for humans to be exposed to. Another power electronic circuit that you might want to include in the vehicle is an onboard charger, so that you could directly connect to an AC voltage source, say in your home, and the vehicle would have all the power electronics necessary in order to convert that AC voltage into the DC voltage that you would use to charge the battery. And this is being led by Professor Miki Banu from Dearborn. So the approaches that we are taking in this project, one is we are looking at different converter topologies, such as multi-port converters. These are converters that have multiple inputs and or outputs that can essentially leverage the same devices. All of these circuits are made out of sort of the same basic components: transistors, inductors, capacitors, just in different topologies. But if we can combine those topologies, we can utilize these components in multiple ways to achieve multiple objectives, and hence reduce the overall number of components required for implementation. Another topic that's being pursued are what are called matrix converters. These are converters that directly convert AC from one voltage and frequency to another voltage and frequency directly without the need for a DC interface. That can also be used to reduce component count as well. Yet another idea is the phases of the electric motor are essentially what we call inductors. And hence we can actually use those as components in the power electronic circuit. So here's a picture here that illustrates a concept we're looking into, which is developing an onboard battery charger, actually using the motor inductances as part of the circuit itself. In addition, we have a work going on looking at taking these integrated circuits and looking at the packaging related to implementing these and then the thermal management of these circuits as well. Then the third project is looking at developing low-cost inverter technologies. So we have the US Drive roadmap here, which is saying that in 10 years we need to increase the power capabilities of these drives by about 50%, reduce the cost per kilowatt of these drives by about 50% as well, right? These are very aggressive goals to achieve. And so this project is attempting to accomplish this, one, by using wide bandgap semiconductors, but then also designing the packaging and the thermal management, and potentially integrating the capacitors associated with the inverter into the overall package as well. So here's a picture which kind of illustrates some of the goals of this particular project. We are looking at a dual cooling. So typically you're cooling the transistors shown in the center on one side, looking at actually trying to extract heat from both sides of the semiconductor devices, looking at different thermal interface materials such as a diamond, which has good thermal conductivity, but also can be used as an electric insulator as well, and replacing bond wires in the which perform the connections between the semiconductor devices and the rest of the system. Those bond wires have some significant inductance and significant resistance, and so replacing those with direct metal connections as well, and looking at different ways of achieving these metal bonds through sintering, soldering, paste, so on and so forth. forth. So we have a lot of activities going on right now. This is just a brief overview of what we're doing. And at this point, I would like to turn it over to Professor Yiyang Li.